Я говорю по-русски. No, thank you. But sorry, it's a lie. It's in fact the only Russian sentence I've learned 20 years ago. And yesterday night, someone told me I could make it true by saying «не говорю по-русски». So I'm making progress, and I expect myself to be fluent in Russian just after we've finished terraforming Mars. So for today, I will continue in English. So hello, thank you for coming to the talk. I don't expect you to know me, but if you do, you know that usually my talks have a very cryptic title that doesn't really reflect the content of the talk. And today is sort of an exception because I will be talking about typeclasses, then typeclasses derivation, and how we do that with SchemaZ. So it's pretty much the title. So, and also before getting into the content, I must warn you, I will probably say a few inaccurate things because I'm not a teacher, I'm just a guy with a suit. And also, he's not there, but thank you, John, for ruining my talk by saying that typeclasses are snake oil this morning. So, what are typeclasses? My very simple definition is that a type class is a generic interface parameterized by a type, and that we provide implementation of this interface by constructing a value rather than adding some method to a type. And also, something very important, but that's not always the case, it's that a type class should have laws. But in fact, we almost always abuse the term and refer as type class to something that doesn't have really a law. So, for example, this example is not really a type class because it doesn't have laws, but it's simple enough to make it pretty understandable. I hope you can read the code from the back of the room. So we have three elements. We have first the definition of a type class. It's a trait with a type parameter and a few methods. Then we provide instances in the implicit scope for this interface. So here it's the string preprint object. And finally, we can use this type class by requesting an implicit evidence, an implicit instance of the type class, and use it. So that's, for example, this logger can log pretty much anything in the console. Kids don't do this at home, by the way. By simply requesting that we have an instance of prettyprint for the type, and it will use a method in the instance, and it gets the concrete instance by using the implicitly method from the ScalaConf. And also, before we dive into the rest of the talk, just to make sure that we are on the same page, a few words about kinds. Who has already seen this syntax for talking about kinds? Okay, cool. It's from Haskell. So star is the kind of the values we use, integers, strings, boolean, and so on. List of strings, for example. Then star to star is the kind of type constructors. So for example, functor, or list, option, and so on, but not that existentially quantified list. And a type class is always something of a kind, something to star. So we have lower kinded type class, sort of, like monoid. It's from kind star to star. And we have higher kinded type classes like functor itself is the type class functor, not a functor, but the type class functor is of kind star to star to star. That's just some vocabulary, because we'll see a few higher kinds in the rest of the talk. So why are type class so cool? It's because it allows us to implement the type class independently from the type for which we want to implement the type class. It's also very cool because since type class implementations are values, we can easily build bigger implementations using smaller ones. It's compose. And also, when there are laws are pretty cool. So let's see these advantages in more detail. As I said, implementation of a type class is completely decoupled from the type class itself and the type for which we implement it. Meaning that I can add some behavior, some functionality to types I do not own. For example, I can add a method to types of the Scala standard library. I cannot code inside the standard library, but I still can add some functionality to it. That's very important, and that's why it's more useful than, for example, object-oriented interfaces. Type class compose, meaning that I can build bigger, quote, bigger instances out of smaller ones. So for example, I can say, I'm able to pretty print any list of any type as long as this type has an instance for pretty print. And that's what I say here in the code. I take the list, I map over it with the pretty print for the type of the element of the list, and then I make a string, and I get a pretty print for the list. And finally, laws give us the ability to reason about type classes in an algebraic way, meaning that I can build proofs to convince myself that something works. I can use this proof or these properties to write property-based testing, which is much more powerful than just unit testing. And also it means that I can completely forget about the details. As long as something is guaranteed to respect the laws, I can reason about the laws and forget about the details. And in the end, using type classes for an application developer perspective allows us to have business domain that are very, very simple and lean. I have no methods in my classes, it's pure data, and I will add all the behavior using type classes. For example, that way I can have, in a very big project, I can have a domain that is shared by different modules, and these different modules, they have the same language, the same domain, but they can implement some functionality differently depending on the context. So that's a very useful tool in our developer toolbelt that we couldn't have had with, for example, object-oriented programming. But still, I have to implement these instances. If something changes in my business domain, I will have to change my type class implementation, my type class instances. And that's quite a lot of work. So that's why we want to be able to derive instances of type classes automatically, because we are very lazy, right? I am, at least. So when I talk about type class derivation, I talk about a way to get or provide instances for type classes automatically. And for the rest of the talk, and in many type class derivation library, we will restrict ourselves to instance of type class of the kind star to star. There is, for example, kittens that allow to derive instances for higher kinded type classes, but that's not the subject of the talk. So there are, in fact, many derivation libraries out there. I didn't list all of them, but the most popular. SchemaZ deriving might not be the most popular, but I put it in first for a reason that might become obvious later. And then, of course, we have Shapeless, although everybody has heard about Shapeless, yeah? And Magnolia, that solves some of issues with Shapeless. So let's take a look at these different libraries very quick. So SchemaZ deriving takes a pretty original approach to type class deriving. It builds upon the algebraic structure or properties of the type class themselves. It uses a bunch of other type classes, higher kinded type classes, namely applicative, alt, divisible, and decidable, which are of the kind star to star to star. But it has some restriction. It doesn't access the names of the fields in the case classes, for example. And because it builds upon algebraic properties of the type class themselves, it cannot derive instances for type class that doesn't have laws. Really, really quick, a few words about these higher-kinded type classes. They all revolve around the same idea. If I get an f of A and an f of B for some type class f, and if f has an applicative instance, that means that f is set covariant, and then applicative out of this f of A and f of B will give me an f of pair AB. Similarly, alt will, for the same type class, give me an instance of f either AB. And if my f is contravariant, divisible will give me the f of pair AB, and decidable will give me the f of either IB. So, thanks to that, if I'm able to decompose my business types in terms of pair and sums, ithers, I will automatically be able to build instances for my ADTs. So that's a first approach of deriving type classes. It's based on the properties of the type class itself. On the other hand, we have shapeless that builds instances from the algebraic property of the ADT itself. So the type for which we want to implement a type class. It defines a generic representation of types using constructs that are HList and coproducts. But it has a series of problems. It can access the name of the field. It doesn't require the type class itself to have laws, but it's slightly complicated. Most of the computation happens at type level, meaning that it's difficult to debug, difficult to test, and also because it happens at compile time, it can blow up the compilation time. And to solve that problem came Magnolia. It's also based on the structure of the ADT, meaning that to derive a type class, we will decompose our types into smaller bits and then compose the instance from this decomposition. It simplifies the development by providing two new abstractions, namely case class in a single word and sealed trait, which is nice, but you have yet another more API to understand. Basically, case class will reflect the structure of a class. So you get the field names, the annotations, and so on and so forth. And the same for sealed trait. It's much, much better for compilation time, but also it's not really easy to test. So that was a very quick primer on type classes and type classes derivation. And now I will talk to you about SchemaZ, which is a library I've been working on for way too long. It's not released yet. Actually, I will show you things that are not yet in the GitHub repository of SchemaZ, so it's really, really fresh. So SchemaZ takes an approach that is similar to Shapeless and Magnolia, meaning that it revolves around a representation of the structure of your ADTs. But arguably, we could say that it unifies both approaches, the ScalaZ deriving from the type class and the shapeless approach from the ADT. And also, it brings a lot more than just type class derivation, but that's outside the scope of this talk. But we can talk about it later if you want. And here is the link for the project itself. So SchemaZ provides an abstraction, what we call a schema, which is something you write side by side with your case classes that represent the structure of it. Then it provides you with a mechanism for deriving type class instances from the schema, and also a mechanism for expressing schema evolution. That's what is beyond the scope of this talk, but it also gives you the way to evolve your ADTs without breaking serialization compatibility. So the architecture is pretty simple. The Z stands for zero dependency, meaning that the core module has zero dependency, and that's what provides you with the schema abstraction and the derivation mechanism. It has a few compatibility modules that will provide derivation for the most popular type classes from CATS or ScalaZ or whatever. And also a generic module that will help you scrap more boilerplate. So for example, inferring the schema from the structure of your ADT using shapeless, namely. So SchemaZ builds upon this realization that, in fact, ADTs are produced by a very, very simple algebra, which needs only three things: the unit type, a binary sum, which is either, and a binary product, which is tuple2. And to convince yourself that it is possible, let's take a look at a few types. So let's say I want to define the bit type. A bit has only two elements, two inhabitants, 0 or 1. And in fact, unit is a type that has only one inhabitant, and either AB has A plus B inhabitants, as many inhabitants as there are in A plus how many there are in B. That's why we call that a sum. So if we do a very quick computation, 1 plus 1 is equals 2. So there are as many inhabitants in either unit as there are in bits. Similarly, for the product, the pair, we could say, for example, a byte is the product of 8 bits. And again, we can calculate the number of inhabitants of this big ugly type on the right and the byte type, which has 256 inhabitants, or different values if you prefer. Here I have, do I have a pointer? No. So bit has 2 inhabitants, so this pair here has, 2 times 2 equals 4, times 2 equals 8, and so on and so forth. 2 to the power of 8, it's 256. And we can go on forever like that. For example, option of A is the same as either unit of A or A. The unit would be known, and A will be A, or some A if you prefer. And thanks to isomorphism, we are able to bind together this very simple but cumbersome representation to our concrete types. So for example, if I want to prove that I can represent booleans using either unit, I just have to provide an isomorphism, which is just a pair of functions that goes both ways. So if I get a bit, which is either unit, I decide, for example, that left is true and right is false, and I can go from either unit to my boolean. And the other way around, if my boolean is true, I return left of unit, and if it's false, I return right of unit. So far, so good? Yeah, cool. So now imagine I have a very simple domain model with a sealed trait and 2 implementations, and a case class person that use values of that sealed trait. So, for example, if I want to define the schema for the case class person, all I have to do is, provided that someone already has built the schema for role, all I have to do is say, okay, my case class, this is this first combinator, has 2 fields, name and role. The arrow allows me to label the schema prim or string schema, the schema for the string field with the name of the field, which is name. This colon star colon allows me to define a product. And so in the end, I have a product of 2 fields. Fields are just types with a label. And if you squint hard enough, you will recognize that this has exactly the same structure as this. But this represents a pair string option of role. And what I want is a person, so I have to plug an isomorphism that goes from the internal representation as a pair to the case class person. Still good? Okay. Similarly, sorry it's a little bit small, but it's the same idea with seal trait or union, if you prefer. I have a sum, because my seal trait is a sum type. So provided that someone gives me a schema for user and a schema for admin, I can build a schema for role by just, combining them into a sum, giving them names, and providing the isomorphism that goes from this either user admin to role. And again, the isomorphism is really simple to write. The generic module will provide you with all that boilerplate, but you can still write it by hand. So now we are getting to something a little bit more meaty. The whole schema, so it has two parts, as we saw. It has the structure that represents the internal representation and the isomorphisms. Here is the definition of the structure. So the type signatures might be a little bit complicated, but otherwise it's really simple case classes. I have a schema for the unit type. I also have a schema for a way to define schema for primitive types. And SchemaZ allow you to abstract over your own set of primitive types. So we don't decide what are the primitive types, you decide. And then the basic constructor. We have a constructor for the sums, the products, fields, and branches that I forgotten on this slide, records and unions that are just the representation of your case classes and seal traits, and also a constructor for sequences, like list or whatever. And these strange f and a type parameters are needed for what we will see later about the derivation that uses a technique called recursion schemes. And again, if we think in terms of kinds, it gets a little bit more complicated. This schema f trait is of kind star to star, the f part, to star, the a part, to star, meaning that you need to feed it with a type constructor and a type in order to get a value type. And finally, the concrete SchemaZ definition, it's a trait that is implemented by the constructor we saw earlier, case class, seal trait, optional, and so on. It takes a type parameter, which is the type that is represented by the schema. It has an abstract type, R, which is the representation. So for example, previously, here, R would be either user or admin, and A would be role. Okay. And it contains two things: a structure, which is it's composed of these things, and the isomorphism that goes from the internal representation to your type. And if you look closely, this structure is in fact expressed as a fix of schema f and r. So what is this fix? It looks a little bit scary. It's called a fixed point type. And its kind, I won't even bother trying to tell it, to spell it. But it's just an implementation detail. It's something we need to use in order to be able to use recursion schemes. But just to give you a sense of why we use that, I think there was a talk about recursion schemes earlier, so probably you're already pretty familiar with that. So if I just build my things around only the schema f type, what happens if I put two units, so the one f here, inside a sum? What's the type of this thing? It's schema f of something and either unit. So without the fix, the structure surfaces on the type and we never get a uniform or a homogeneous type. Every schema would have a different type. But with fix, if we wrap everything with fix, we end up with something of type fix of SchemaF, either unit. So that's why we need the fix. So we want to go that way in order to use the technical recursion schemes, and I will not expand too much on that. But basically, recursion scheme is a way to abstract over traversing recursive structures, and it uses 3 ingredients. The pattern functor, so here it's our SchemaF, a fixed point type, or a fix, and more importantly, that's what we will be writing, algebras and coalgebras that explain what we want to do with each element, if constituent, of the schema. So this is true in general for recursion schemes, but we are acting one kind higher. So instead of having a pattern functor, we have a pattern higher order functor, which is this ugly thing. And I don't expect you to parse this code, but it's just as usual as with a functor, but instead of having functions, you see a functor as a map function. You pass it a function and it will apply it to what's inside a functor. Here, an H functor needs a natural transformation because what's inside is already a type constructor. So functor is for the kind, talks about the kind star, and here we talk about the kind star to star. And arrows in the kind star are functions. Arrows in the kind star to star are natural transformations. But otherwise, it's all the same. So to derive an instance using that, what we need to do in SchemaZ is to pick a scheme, so a way to traverse this structure. And in 90% of the cases, it's what we call a katamorphism. It's the simplest one. We need to write the required algebra or coalgebra, and we wrap that up in what we call an interpreter, provided in the implicit scope. And once we've done that, I will show that. Once we've done that, we just derive instances by calling my schema to my type class. So the important bit, what we have to do in order to derive a type class is to write this algebra. And it's a natural transformation, but it's really, really simple to implement. Can you read the code from behind? Yeah. So all I have to do is implement this natural transformation by simply writing a pattern matching that will take all the cases of my SchemaF trait, and I just explain what to do with each constituent. So let's implement a derivation for ScalaCheck gen. So something that will give me a ScalaCheck generator for any possible type that has a schema. Well, what I have to do, I need some way to transform to generate my primitive types, because me, SchemaZ, I don't know your primitive types, so you have to give me that. And then it's really simple. For a primitive, I use the natural transformation you give me, the prim to gen. For a product, I just generate the left branch, the right branch, and I return a pair. For the sum, I just pick either the left branch or the right branch at random, and so on and so forth. It's really simple. For the sequence, I use gen.listOf. Fields and branches are just labels on top of a type, so I have nothing to do. And for one, I just return unit, because that's the only thing I can return. What will happen is that when you apply that to a schema, the recursion scheme part will go all the way to the leaves of your schema, generate the primitives, because on the leaves you have primitives or units, and then it will climb back up by combining the smaller bits into bigger gens. So in the end, you end up with a generator for your representation. So you have a gen of an either of blah, blah, blah. And thanks to the isomorphism you provided with your schema, I can transform this gen of either some blah, blah, blah into a gen of, say, person or whatever. So that's the only thing you have to write. It is very, very testable. It's a simple function. You can generate schemas at random and do property-based testing on your type class derivation. It has exhaustivity matching, so the compiler will tell you if you forget a case. It's arguably very, very simple, and the usage is also very simple. So I hope I convinced you that it's indeed very simple. Did I? It wasn't simple to write for me, the library author, but for you, the user, it should be pretty easy. But it's not always that easy. There was a bug in the gen I just showed you. Can you spot it? You want me to show the slide again? Yeah? The bug is somewhere there. No, it's good, because element here is already a gen for your type. Oh, it's always list for the moment. Yeah, it's a limitation for in the current version. But it's a little bit. It's two lines above. Well, I'm running out of time, so I will give you the solution. The thing is, our sums are nested, right? It's binary sums. And we used one off, which means that for each pair of branch, we had the same probability to go either way. So if we have this seal trait with 4 subclasses, we will produce the foo in half of the cases, in a quarter of the cases the bar, and in the remaining eighth of cases, the bars or the cuts. That's because it's not flat, it's this binary thing. But there is a way to get away with that. ScalaCheck has this frequency method where we can give weights to the different choices. And so we should be able to have a gen that will be fair and produce 1/4 0.25 probability for each case. It's in fact pretty simple. All I have to do is to say, okay, I will not derive a gen directly. I will derive something that is a gen labeled with a weight. And what I can do is I keep all the cases the same. I just wrap them in a pair with 1. It's the weight of each branch. Most of the time it doesn't mean anything. And in the case of the sum, when I get to the sum node, I get 2 pairs, one for the left and one for the right, and each one has a weight. So I can use that as a frequency and say to the level up, okay, my weight is now the sum of the weights of my 2 branches. It gives something like that. And so when the katamorphism see this tree, it goes all the way down, produces a gen for that, for both branches, gives them the weight 1, and then it goes 1 level higher and says, okay, this whole thing now has the weight 2, and the other one has the weight 1, and again, it goes 1 level higher, this whole subtree has a weight 3, and this one has 1. So in 1 in 4 cases, I get foo. And in the 3 other remaining cases, in 1 in 3, I get bar. And in the 2 remaining cases, in 1 of 2, I get bars. And in 1 of 2, I get cuts. So that's it. I have a fairly distributed gen. So most of the time, deriving with SchemaZ is pretty easy, but sometimes you have to think a little bit harder. But the cool thing is, with recursion scheme, once you get used to it, everything is possible. It's just a matter of scratching your head a little bit more. And still, you keep the testability and the exhaustivity checking and so on. And to finish, oh, I'm just in time, perfect. I will get back to what I claimed earlier, that SchemaZ unifies ScalaZ derivings and shapeless approaches by showing you something we have in the library that automatically derive a type class if your type class has an instance of alt or decidable, depending on whether it is covariant or contravariant. If you can see the code, sorry if you cannot, here I derive a type class I derive the type class H, and the only thing I know about H is that it has a alt instance. And we use alt, the method in alt, in the sum and the product case. So for sum, we use either 2, and for product, we use tuple 2. So if you get a type class, a lawful type class that has an alt instance, as God intended, you will get your derivation for free. And if your type class is contravariant and you have a decidable instance, you will get it for free. I didn't show it on the slide, but that's the same idea. So, if you want to, that's pretty much it. If you want to dig deeper in type class derivation, I cannot recommend hard enough reading the chapter 8 of Functional Programming for Mortals with ScalaZ by Sam Halliday. It's an excellent book. Everybody should read it. You can also look at the actual SchemaZ code and see that I have simplified quite a bit to fit in the slides. And also you can ask me anything. I'm on Twitter, my DM are open, and I'm always happy to answer questions. So that's pretty much all I have, but since I am on stage and you're captive, I wanted you to take a few minutes to take part of the Scala Thank You campaign on Twitter. It's a campaign launched by Daniel Sfregola, and the idea is to send a bunch of tweets to thank people that helped you, or organization, or even libraries, sorry, that helped you in your Scala life. So please do that. It will bring a lot of positivity to the community. And also I really lie to you because there is another thing I can say in Russian, it is спасибо.
У нас осталось время, да, на один буквально вопрос. Вот я вижу этого человека, который спросит.
Thanks. I guess the first question that comes up to mind when people see things like that is performance. So do you have experience of running it in production, or maybe some benchmarks? Because like this is always a questionable thing when you see these like transformations of these ADTs and stuff like that.
So I cannot really answer the question because, as I said, the library is not released yet. So we never tried it on a real-world application. The cool thing is that I can guarantee that derivation will have absolutely no cost at compile time. For starters, it will happen at runtime. Actually, the derivation itself should be pretty fast because it's merely a traversal of your schema, and I suppose you don't have schemas that will take megabytes. The performance of the derived type classes might probably be inferior to what you could have with shapeless because we are going through this intermediate representation. There might be a way to avoid that, but I'm not sure it will work. And I'm even more, maybe it will work better with Scala 3, but with Scala 2 it might have a small impact. But honestly, I cannot tell you how big an impact it will have.
Yeah, I see. So you would not recommend it, so far at least, to use in a hot path code, like for high performance code, right?
If it's really high performance, probably not. But as I said, always when it comes to performance, first take some measurements. And also, you cannot use it because it's not released yet. So.
Еще раз скажем спасибо Валентину.
Thank you.
И приз уходит единственному спросившему.